Welcome to our channel Biswanka'smathexclusive Math Exclusive. This video is on expansion of function. If you like my video, please subscribe our channel and tell your friend for also subscribe our channel. Let's start. Expansion of function. Continuous at a point. When we said the function is continuous at a point, when the limit x tends to a minus fx equals to fa equals to limit x tends to a plus fx, where this is left hand limit, this is right hand limit, and this is functional value without any calculation. Its another form is, for given epsilon greater than 0 be arbitrary, there exists delta such that mod of fx minus fa less than epsilon for all x. When x minus a, that is mod of x minus a less than delta, that is plus minus fx minus fa less than epsilon, that is fa minus epsilon less than fx less than fa plus epsilon. Now continuity at a interval ab, closed interval ab. Limit x tends to c minus fx equals to fc equals to limit x tends to c plus fx, where c belongs to open interval ab. Now continuity at a point in closed interval ab. This a point. Limit x tends to a plus fx equals to fa, and continuity at b point in closed interval ab. Then limit x tends to b minus fx equals to fb, and here x tends to a plus. Bounded. When we said bounded, every continuous function is bounded, but the converse not always true. Supremum and infimum. Small f less than equals to fx less than equals to capital M, where small m is the greatest lower bound and capital M is the least upper bound, that is LUB, and this is GLB, and this is called infimum and this is called supremum. Differentiability. Differentiability implies continuity, but converse not always true. Capital L, f dash a equals to limit h tends to 0 f a minus h by h, or f dash a equals to limit h tends to 0 f a plus h minus f a by h. If left hand limit, that is L f dash a equals to right hand limit, that is R f dash a equals to 0 or a finite quantity or plus minus infinity, then we say that fx is differentiable at x equals to a. However, we try to avoid plus minus infinity. Rolle's theorem. Here I only state the statement portion. Rolle's theorem. Statement. Let fx be a function of x defined in closed interval ab such that number 1, fx is continuous in ab, number 2, f dash x exists in ab, number 3, fa equals to fb, then there exists at least one point c in open interval ab such that f dash equals to 0. Here I put a note. Number 1, these conditions 1, 2, 3, that is this above conditions, these 3 conditions are sufficient condition but not necessary. Number 2, from f dash c equals to 0, we conclude that x equals to c is root of the equation f dash x equals to c. Now start with example. Example 1. Is the Rolle's theorem applicable to fx equals to tan x in 0 to pi, closed interval 0 to pi? This is the tan x graph. From this graph we also see that limit x tends to pi by 2 minus fx not equals to limit x tends to pi by 2 plus fx. So fx is not continuous at x equals to pi by 2. Thus the Rolle's theorem be not applicable in 0 to pi, in the closed interval 0 to pi. Is the Rolle's theorem applicable to fx equals to 4 minus 6 minus x whole to the power 2 by 3 in the closed interval 5, 7. Now f dash x equals to get 2 by 3 6 minus x whole to the power 2 by 3 minus 1, that is 2 by 3 1 by 6 minus x whole to the power 1 by 3. Now f dash 6 minus epsilon equals to 2 by 3 1 by epsilon to the power 1 by 3 tends to infinity as epsilon tends to 0. And f dash 6 plus epsilon equals to 2 by 3 into minus 1 by epsilon to the power 1 by 3 tends to minus infinity as epsilon tends to 0. So f dash x does not exist at x equals to c. Thus the Rolle's theorem not applicable. So today's topic is end. This is my first video on expansion of function. Next I upload another video on this topic. If you find this video is helpful for you, please like and share and also subscribe our channel. Thank you.